Hello. Okay, so we continue with this problem. The problem is that the function is given as z square minus 1 divided by z square minus 2z, and we would like to find the residual of this function at z equals 2. And if we factor out z from this expression, we see that z equals 0 and z equals 2 make denominator 0. It means that these are the simple singularities, but at z equals 2, which is a singularity, isolated singularity, we would like to calculate the residual of this function. So by definition, the residual of the function, okay, is found by residual of the function at 2 is given as limit as z approaches to 2, okay, z minus 2 times the function. As you see, what we are doing is that, as before, this is the problematic case, right? So we multiply this function by that, and then just evaluate the function at z equals 2. So what it means that if you get z minus 2 away from the denominator, you get z square minus 1 divided by z, and it is to be calculated at 2, z equals 2. As you see, it gives you 4 minus 1 divided by 2, which is 3/2. So the residual of this function at z equals 2 is just 3/2. But what about the residual of the function at z equals 0? In this case, we multiply the whole function by z so that this singularity goes away, and then simply we just can say that this residual of the function at z equals 0 is simply given by z squared minus 1 divided by z minus 2, because this z is cancelled from the product. Okay, it will be in front of fc just like z minus 2, and then we will set z to 0 in this expression. So it will be just minus 1 divided by minus 2, which is 1/2. So we will show that this function, the integral of this function, will be 2 pi I times just the total residual. So the integral of this function, which is z squared minus 1 divided by z squared minus 2z, okay, times dz, will be equal to 2 pi I times 3/2, which is the first residual, plus 1/2, which is the second residual, which gives you 2, which is 4 pi I. The result is 4 pi I. As far as this curve C continues, z equals 0 and z equals 2. Z equals 0 is in the middle, z equals 2 is on the real axis. As you see, C is any curve which contains these two singularities. If this curve did not include these two singularities, or just included only one of them, suppose like that, okay? So it included only the singularity at z equals 2. In this case, the total residual will be just 3/2 instead of just the summation of the two. But if the residual, if the curve was such that it included only this z equals 0 singularity, then the result would be, the residual would be just 1/2 instead of 3/2, so that we would have different result. And also, as I told you, if C is somewhere else which doesn't include the two singularities, then the result is going to be totally 0. Okay, so this is interesting. So this method is extremely powerful in calculating the complex integrals. Okay, good. So now I would like to solve some more examples. Okay, I would like to solve some more examples. Okay. So in the next example, we would like to get the residual of this function. Fz is given as z squared divided by z minus 2 times z squared plus 1. Okay, so after finding this, of course, we can calculate this integral. Okay, so we can calculate what was it? It was just equal to 2 pi I times the total residual. Okay, but in order to find the residual, we have to find the singularities which make this denominator 0. But this is easy because z equals 2 makes this parenthesis 0. But what about here? It can be plus and minus I. Why? Because z squared plus 1 can be written as z minus I times z plus I. So it can be written like that. So as you see, z squared is the first term, and the last term is minus I times I, which is minus I squared, and I squared is minus 1, so it's plus 1. And the intermediate terms will just cancel each other due to 1 plus 1 positive. So basically the singularities are just z equals 2 z n plus n minus I. Okay? So now we would like to get the residual at 2, the first one. So it means that this is the problematic denominator. So we just multiply the whole function by that and just consider the rest, which is just z squared over z squared plus 1, and we calculate this at z equals 2. So when you do this, you will get 4 divided by 5. So 4 over 5 will be the result for the first residual. Okay, 4 over 5. What about the other residual? Okay, so the other residual is one of them. So let's consider z equals plus I. Okay, so this was z equals 2 now. For z equals plus I, it means that we will get rid of this parentheses from the denominator, but just get everything. So residual of the function at I plus I is just nothing but the function given by z squared divided by z minus 2. Okay, this is gone and this survives, z plus I. Okay, z plus I. And z is to be replaced by I. So in this case, I squared divided by I minus 2, okay, times 2i. 2i. Like I here, and there is one more I, 2i. So this cancels one of the i's over there, and there is I minus 2, but we don't like complex number on the denominator, so we multiply the top and the bottom by I plus 2 there, and I plus 2, okay. In this case, this will be equal to I times I plus 2 on the top divided by this 2 is here, I minus 2 times I plus 2 will give you just, okay, I minus 2 and I plus 2 will give you I squared minus 4. Okay, so now this I squared is minus 1. Okay, so this minus 4 there is minus 5. So the whole thing is minus 5 there. And then it's equal to this I times I is I squared, which is minus 1. And then plus 2i on the numerator, and denominator is 2 times minus 5. So it's just 10 with a minus sign. So this minus sign makes this plus and this minus. Okay, so 1 minus 2i over 10 is going to be the result for the singularity at z equals I. We will repeat now the same thing for z equals minus I. Okay, for z equals minus I, again, we calculate the residual at minus I, and now we get rid of this term, because this term is now giving us headache. So the rest will be written. So we get z squared divided by z minus 2 times z minus I. Now, all z's should be replaced by minus I. Okay, so all the z's will be replaced by minus I. But it's minus or plus, z squared is just I squared on the top divided by minus I, okay, minus 2 there, and then minus I, another minus I is just minus 2I, and as before, these two, one of the i's will cancel, and then these minus signs will cancel. We get I divided by just 2I plus 2. Okay, this minus sign makes this positive, and everything is gone, and 2 is on the denominator here. Okay, so as before, we have to really get rid of this I plus 2 from the denominator. So what we do is that we multiply the top and the bottom by just written this as 2 plus I. Let's write it as 2 plus I. Now we multiply this by 2 minus I, and numerator is also multiplied by 2 minus I. Okay, this is the property. We don't want to get anything, any complex thing on the denominator. So the top is 2I minus I squared, okay, because of the product of these two, divided by, now it's just 2 there, and then 2 plus I, 2 times 2 is 4, okay, and will be 1, okay, because minus I squared will be minus 1, and there is minus sign, it will be just 1, 5. So it's just the same thing as 10, but this is minus 1, so it's 1 plus 2I divided by 10. So basically, we have this result. So if the curve C includes all these three residuals, then the result of this function, okay, the integral will be equal to 2 pi I times the residuals. Just add them up. 4 over 5 is the first one, plus the second one, and the third one. So when we add them up, 2 i's will cancel, as you see. Okay, 2 i's will cancel because one is minus, the other is plus. 1 over 10, 1 over 10, 2 over 10, which is 1 over 5. So 1 over 5, this is 5 over 5, which is 1, which is just 2 pi I. So the result is just 2 pi I. Okay, so we just completed the whole example, okay, and the result is just 2 pi I. Okay, we can now go to another problem, okay, because the more problems we solve, the better understanding we will have. So we will go problem by problem, okay, so the equation will be kept there, okay. All right, so the next example is cotangent of z. So fc is equal to cotangent of z. So let's find the residual of the function at z equals 3 pi. At z equals 3 pi, this function will blow up, right? So because cotangent z is 1 over tangent, or just cosine z divided by sine z. As you see, wherever z is 0, sine z will be 0, and then it will be the pole, or just singularity. But now they want you to find the singularity at 3 pi. So now, how do we get this? How do we get this? Now, the function f of z is written as cosine z divided by sine z. Okay, and now for z equals 3 pi, we will write now the residual as this. Remember, f 3 pi is equal to limit as z approaches 3 pi, we multiply by z minus 3 pi, as if there is a denominator, and then denominator had this z minus 3 pi, but it doesn't actually. Then this times cosine z divided by sine z. Okay, sine z. Now, what is that? So if you put this z, now let's look at this thing. Okay, so we can now think this ratio as, it looks like there is a problem because this didn't get rid of this sine z on the denominator. So what can we do? But now look what's happening. So as limit goes, z goes to 3 pi, we can now consider this as okay, as z minus 3 pi, okay, over z minus 3 pi over sine z, okay, this part, we consider only this part, okay, and then we consider the other part, okay, so cosine z remains. So now let's consider, so limit, so times this times limit, okay, so the problematic part is just, okay, removed from this part, and this limit as z approaches to 3 pi cosine z, we can calculate this, okay, we can calculate this part, because now if there is the limit of the product, it's the product of the limits, so basically this property, this now gives you just -1, this gives you -1, but now look what's happening here, this what's happening. So this can be written as limit, okay, with a minus sign is right there. So the result is just minus limit as z approaches 3 pi, z minus 3 pi over sine z. Now, as you see, at z equals 3 pi, this is 0 over 0. Okay, this is 0 over 0. This is undefined function. In this case, we can use L'Hopital rule. Okay, L'Hopital rule. According to the L'Hopital rule, we can take the derivative of the top and the bottom separately, independently, and use this limit until we get non-zero thing. So the result is now minus limit z approaches to 3 pi. The derivative of the top is just 1, and the derivative of the denominator is cosine z. Okay, now the result is cosine 3 pi is -1 as before. It's just 1 over -1 is -1. There is another one minus sign, so that the result is 1, basically. So residual at f equal 3 pi happens to be just equal to 1. So this is the result. This is the result. So once we calculate this, but now, as you see, the result, if we want to get the integral of this function from -infinity to +infinity, or just around a closed curve, then we have to consider all the residuals. But now at 0, there are infinite number of residuals. Okay, one is 0, the other is plus and minus pi, plus and minus 3 pi, plus and minus 5 pi, and so on. As you see, there are infinitely many number of residuals for this case. Okay, so that's why the result will be also including the sum of all these residuals, which is not our purpose right now. Okay, now we continue with another example. The more examples we solve, the better understanding we will have. Okay, good. Okay. Now, we have this function. Now, in this example, the function is given as z squared plus 4 divided by z cubed plus 2z squared plus 2z. Somehow, we should be able to get the zeros of this function on the denominator. So, okay. So now find the residual at each pole point or singular point and calculate the integral. So this can be written as, okay, z squared plus 4 divided by z, factor out. You have z squared plus 2z plus 2. So this is on the denominator. In this case, we can just write this as, okay, we can just write this product as, this one as, okay, z plus 1 minus I times z plus 1 plus I. Okay, let's check if this gives you exactly the same result. The first term is z squared, and okay, z squared. If you multiply with z squared, and the other one is z, okay? So we're just multiplying each terms by the terms on the right. So plus z plus I, now this plus z, okay, plus 1 plus I, and then this one minus iz minus I, and another minus I square, which is just plus 1. Okay, so what happens is that this, okay, this 2, okay, this z here, I plus, this one was just z, this is just z plus I. Anything canceling? No, actually, this is not the case. So probably, okay, this is not the result. Because the book has written the result was this, but actually it's not. So let's do this. Z plus, okay, z plus 2I, and then let's multiply by z. Okay, let's check if we can really get this result, if this is correct or not. Let's check it again. Z squared plus z, okay, plus iz, okay, iz. So this term was going to be iz, okay. Now, probably correct. Now, if you multiply the second parenthesis by 1, it's just z plus 1 plus I, it's correct. But by minus I, minus iz, minus I plus 1. As you see, iz's will cancel each other. And then we have 2z, z plus z is 2z. And then plus and minus i's will cancel. 1 and 1 is 2. Exactly, we have this result. So basically, this function can be, okay, written as, just z squared plus 4 divided by z times z plus 1 minus I, okay, times z plus 1 plus I. How could we get this 1 minus I and 1 plus I as the root? It's simple, because remember that this second order equation, for this second order equation, if you set this to 0, 2z plus 2, you can get the roots by this minus b, which is minus 2, plus and minus square root of b square minus 4ac, which is 4 minus, okay, 4 minus 4ac. A is 1, c is 2, it's 8 divided by 2a. Now a is 1, it's just 2 divided by 2. Okay, but now this is minus 8, and this is 4. So we get minus 2 plus and minus square root of minus 4 divided by 2. Okay, so this minus 4 goes like this. So this 2 cancels this, and 4 goes out as 2, so that there is nothing on the denominator. Minus 1 plus and minus square root of just minus 1. But square root of minus 1 is just I. So minus 1 plus and minus I will give you the result. So so the root will be minus 1 plus I, or root minus 1 minus I. So that when you subtract these are, so you will get z minus 1 of the root, z0, and then z minus the other root, z1. Okay, one is minus 1 plus I, the other is minus 1 minus I. So that these minus signs cancel the minus sign in front of 1, and then this is what you get. So this is how you can get the roots if it's second order. But if it is third order, then it may not be that easy. So you have to really apply some different techniques. This is what is happening now. Okay, so now having determined the denominators, now we can find out where the poles are. Z equals 0 is one of the first singularity, because z equals 0 makes this denominator 0. Now, when z equals, okay, minus 1 plus I, this blows up, because it cancels these two terms and then it becomes 0. This is the one. And for the third one, this one, z should be equal to minus 1 minus I. In this case, this will blow up. So we have three singularities. Now, if our curve is including all these, let's see where they are. Okay, let's put this in complex plane. This is real z, and this is imaginary z. Okay, so z equals 0 is in the middle. Minus 1 plus z, is real is -1, which is this side, and plus I is right there, so that it's this point there, okay? Now, -1 minus I is exactly symmetric this point, okay? If our curve includes these three singularities, then we can calculate this function after having determined what the residuals are, independent residual. Let's get the simplest one, z equals 0. So now when z equals 0, now except this one, we will get all this, we will calculate the function at z equals 0. So z squared plus 4 divided by, okay, z plus 1 minus I times z plus 1 plus I. Now z is to be replaced by 0 in this case. Now, the first one, z equals 0 case. The residual will be equal to 0 plus 4 divided by 1 minus I, and then when it is 0, it's 1 plus I. But it's just 2, as you see. This just product is just 2. So 4 divided by 2 is just 2. So the first residual happens to be equal to 2. Now let's calculate the residual at z equals -1 plus I. Okay, the second one. So for this one, we get rid of now this one, but write all the others. So the residual will be equal to z squared plus 4 on the top divided by, okay, except this one, z times z plus 1 plus I. Now z is replaced by this, but now it's going to be a little bit complicated, okay, because now this will be equal to -1, okay, -1 plus I squared plus 4. This is just the numerator, as you see. On the denominator, we have -1 plus I multiplying -1 plus I, which is just 2I. Okay, because -1 cancels this, we get just 2I. Okay, let's check again. If z is equal to -1 plus I, okay, this cancels and then get 2I. That's right, that's correct. Okay, so now we have the square of this, we have to square this, so this residual will be just 1 minus 2I plus I square is the square of this parentheses plus 4 there, and denominator will be just 2I multiplied by that, but this is just this is -1, don't forget. The first term is just -1 sitting there. So if it is multiplied by 2I, 2 is outside, just keep this as a parenthesis. Now I times I is -1 and minus I, okay? So minus I minus 1. Where did this one come from? Because I times I gives you I squared, okay? I squared, and then I squared is just -1. So 2 is outside, we have this. Now, as you see, this cancels that because I squared is -1, and we have now equal to 4 minus 2I divided by, okay, minus 2 on the denominator, just 1 plus I. Now we have to get rid of this 1 plus I on the denominator. This 2, by the way, cancels this, and then we get 2 minus I divided by 1 plus I. Now this is multiplied by 1 plus I, the top and the bottom. Okay, 1 minus I, sorry, minus I, to get rid of this thing on denominator. So the denominator is 2, so it's just this times that. So 2 minus I times 1 minus I divided by 2. So now let's multiply this and see what we get. 2 times 1 is 2. 2 times minus I is minus 2I. This is another 1I minus 3I, and minus I is just -1 divided by 2. So it's just now 2 minus 1 is 1. 1 minus 3I over 2. So we get 1 minus 3I over 2, okay, with a minus sign. Let's check. Yeah, we forgot the minus sign there. Okay, the minus sign. Okay, so one of the result is this, one of the residual belonging to the singular point minus 1 plus I is this. The other residual will be similar to this one. So Z equals now, this residual is now minus 1 minus I. Okay, in this case, we get rid of this one now and calculate the rest of this function at Z equals this value, and then it gives you exactly the same thing with plus 3I. Now for this one, the residual is just 1 plus 3I over 2 residual with a minus sign. Okay, so we got all the residuals. Now the integral of this function, including all over the circle or any curve which includes all these three residuals, this here C is given like that, then it's given as 2 pi I times the total residual, which is just the first one is 2. Don't forget the second one, the summation of them is minus, both of them are minus, but now 3I and 3I will cancel each other, so minus 1/2 and 1/2 just 1, and then this will be just 1, the result is just 2 pi I. So all these efforts, tedious algebra, just we ended up with very simple result, which is just 2 pi I. So the integral of this function, okay, when you integrate this, dz, it will be equal to 2 pi I. Okay, over a closed curve, of course. So we found all the residuals which make the denominator 0, okay, residuals at the points where they make the denominator 0, and then we calculate this integral. Okay. Now another example. The more examples we have, the better understanding we will have now. Okay. So we learned the technique now. We can remove everything. Okay. Now, there is also another method. If we have the function given by Pz over Qz, then we know that this Qz equals 0 makes the function blow up, right? If Z0 is first order singularity, what does it mean? Like Z minus 2, at Z equals 2, this is singular point. Z plus 1, or Z plus I, which is minus I, now singular point is minus I. For all these cases, so singular, first order singularities. In this case, what we can do is that we can just take the derivative of the denominator and set it, okay, just get the residual by, suppose that Z0 is the singular point, then residual of this function is simply Pz, okay, divided by Q prime Z at Z equals Z0. Okay, Z0. Let's give an example. So in this example, we have this function, which is exponential e to the iz divided by cosine z. Okay. Now, as you see, this function blows up at z equals pi over 2. So at z equals pi over 2, of course there are other z values, but now this is the thing. So they ask you, what is the residual at pi over 2? There are also other things, okay? 3 pi over 2, 5 pi over 2, and so on. Okay? So we would like to get the residual at this. So now, as you see, we can say that Pz here is just e to the iz, but Qz is cosine z. Okay, cosine z. But cosine z is 0. Okay, at z equals 0, cosine z is 0. But now what about Q prime? The derivative of cosine with respect to z, it's just minus sine z. Don't forget. Now, if you put z0, then it's going to be minus sine of pi over 2. but sine of pi over 2 is 1, it's just minus 1. So the result is just minus 1. So now in this case, what about this? Pz. P at z equals z equals pi over 2. It's just e to the I pi over 2. Okay? Okay, so again, we have the problem. Pardon. Evet arkadaşlar, yine bir problem oluştu fakat problemi çözeceğiz. Evet, bir saniye. Evet, görüntü gelmiş olması lazım. Evet, tamam. Koyuyoruz buraya tekrar. Okay. Evet, tamam. Okey, ses ve görüntü herhalde tamamdır değil mi arkadaşlar tekrar? Bu sistemde birazcık sıkıntı oluyor. Bunu düzelteceğiz artık. Okay. Now, don't forget, we calculated P and Q prime, which is just e to the I pi over 2 divided by just minus 1. So residual of this function at z equals pi over 2 is given as just e to the I pi over 2, okay, I pi over 2 divided by Q prime at pi over 2, which is just minus 1. So now it's equal to minus e to the I pi over 2. But you know the property of this complex exponential function, okay, is that it is equal to now minus sine cosine pi over 2 plus I sine pi over 2. Okay, so this is how you can write the exponential function, as you will remember. Okay, so cosine pi over 2 gives you 0, but this gives you 1. It's just I and then minus I. So this is it. So the residual at this point is just minus I. Okay? We found the residual. Also, we can find, for instance, this function also blows up at 3 pi, right? What about the residual at z equals 3 pi over 2? 3 pi over 2. Can we get this residual at 3 pi over 2? The answer is yes again. Because what we will do is that e to the I z and divided by cosine z, the derivative of this is sine z with a minus sign, okay, with a minus sign, and now z is to be replaced by 3 pi over 2. This is what we are doing. So don't forget, this is the denominator, the derivative of the denominator. Now this is equal to minus sine of 3 pi of 2 is, okay, let's check. This is pi over 2. This is 2 pi over 2, 3 pi over 2, which is 1, okay, plus. So this is plus 1. So it's again minus e to the I z, but now z is 3 pi over 2. So it's now minus cosine 3 pi over 2 plus I sine 3 pi over 2. As you see here again, this cosine cancel, and we get sine. It's just minus I. Okay. Let's check. Which one blows up? Okay, sine 3 pi over 2. Okay, so this is pi over 2, 3 pi over 2 here. Cosine gives you cosine gives you 1 with a minus sign, but this sign gives you 0, so that this is just 1. There is also another sign, a minus sign there, so the result is going to be 1, basically. So now this is calculated at 3 pi. Okay, 3 pi over 2. sorry, 3 pi over 2. Did we get, let's check again. Which one cancels? 3 cosine of pi over 2 is 0. Cosine of 3 pi over 2 is also 0. So, sorry, this is the term which is 1, but this is 1. It's just minus I again. The same thing. But if we want to get residual at z equals 3 pi, for instance, then the result is simply, okay, e to the iz divided by sine 3 pi. But as you see now, this gets another singularity on the denominator. So this blows up. So let's check now. Let's check. Fz is given as e to the iz divided by cosine z. Okay. If we put 3 pi, cosine 3 pi doesn't give you 0, and then you can just insert. Okay. Because at z equals 3 pi, this doesn't blow up, because cosine of 3 pi is just nothing but minus 1. So that it's just minus 1. So minus 1 times e to the I, 3 pi. 3 pi I. So it's just equal to minus cosine 3 pi plus I sine 3 pi. Okay? This goes away. In this case, this is minus 1. Another minus 1, the result is 1. As you see, for some cases, for instance, this is not the singular point, right? This is not the singular point. But if this is not the singular point, the function can be just, this function can be just evaluated at this value, and then it gives you 1. So you don't need to get in residual for this, because it's not singular point. Okay. So let's jump to another example. Okay. Now, suppose that we have now on the denominator the power of z minus z0. The power n. It can be squared, the cube, or the 4th power, 5th power, and so on. In this case, the residual is given as, okay, at z0 is given as limit as z approaches to z0, 1 over n minus 1 factorial, okay, times d to the n minus 1 divided by d, z to the n minus 1, okay, times z minus z0 to the n times f z. As you see, again, we get rid of this by multiplying the function, but the rest of the function, except this, which is just g, this is going to be just g, right? This is just g. We take the derivative, okay? But this derivative, when n equals 1, it was defined, but when n equals 2, it's the first derivative of g, and then if n equals 3, it's the second derivative of g, divided by, of course, 2 factorial, 3 factorial, okay? So you have to be careful with this thing. So now, this is simply a very nice method that we can use when there are some other powers on the denominator, other than just 1, okay? So now in this example, let's see what we have. Fz is given as z squared minus 2z divided by, okay, z plus 1 squared times z squared plus 1, 4, z squared plus 4. As you see here, this is the square of this very simple function which blows up at z equals 1, minus 1. So z equals minus 1 is the second order singularity, because there are 2 of these. So it's z plus 1 times z plus 1. It means that minus 1 is second order singularity. But here, this can be written as z plus 2i and z minus 2i. Okay. So from here, we can see that z equals -1, z equals minus 2i, and z equals plus 2i are the poles or the singular points for this example. Okay, now don't forget, this is the first order, but this is second order. So let's handle the first orders. Okay, now number one. So z equals minus 2i singularity. It means that this term will just go away by multiplying. All the rest will be written. So the residual for this one of the function at minus 2i will be given as z squared minus 2z divided by z plus 1 squared there. Okay, it will be there times this, because this was gotten rid of. So z minus 2i. Okay, z minus 2i. Now z is going to be minus 2i. So if you put this, minus 2i squared is just 4i squared for this case, plus 4i, because z is 2i with a minus sign, is plus 4i divided by, okay, this z plus 1 will give you 1 minus 2i squared, okay, times minus 2i minus 4i. 4i there with a minus sign. There is a minus sign here. So as you see, this 4 cancels all these 4s. This becomes -1, but by employing this minus sign inside, it's just 1, okay, minus I divided by, just everything is gone. There is I that you have to be careful with. So there is I on the denominator, and the square of this gives you just 1 minus 4i, okay. 4i squared will give you 4i squared will give you minus 4. Okay, so it's just -3. So this is equal to 1 minus I divided by I times this I is here in the front. Okay, minus 4i minus 3, because minus 4 plus 1 is -3. Now, if I multiplies these two, we get 1 minus I divided by, okay, this I times is -1, just 4 minus 3i. Again, we multiply the top and the bottom by 4 plus 3i, 4 plus 3i, okay. If you multiply, okay, this is what we get, okay. So the denominator is very simple. So residual is for this one is given as 1 minus I still there, okay, times, okay, 4 plus 3i divided by the product, which is 4 times 4 is 16, plus 3 times 3 times 9. So this is how you can get. So as you see, this turns out to be just a simple number. So now the products for the top gives you 4, okay, plus 3i, another minus 4i is just minus I, and then I times 3i is minus 3i squared, but it's just plus 3. So it's 7 minus I divided by 25. Okay, so it's now 7 minus I, everything divided by 25 will be the result. 7 minus I divided by 25. Now, this was the residual for z equals minus 2i. For z equals plus 2i, okay, the residual is given exactly the same, except this minus sign will be replaced by plus sign. Usually there is a symmetry. 7 plus I divided by 25. Okay, so we got all the residuals. When we get all the residuals, we can just integrate this function very simply. Okay, now let's look now what happens to this case. Suppose that the function in this example, the function looks a little bit simpler, but now we have to take many derivatives for this function. E to the 2z divided by z to the 4. As you see, z to the 4 is fourth order. Okay, this is fourth order singular point, which is z equals 0. Z equals 0 is fourth order singular point. So we have to get now, if this is fourth order, we have to get the third derivative of this, right? Fourth order. So n equals 4. So dn minus 1 over dzn minus 1, which is right in here, gives you just d cube over dz cube of this function, which is z to the 4. Of course, you take the derivative only of the function e to the z, okay, e to the 2z, e to the 2z, okay. So the function e to the 2z, whatever is on the numerator, because you get rid of this, right? But because of this product, and then just g is there. So whatever g is, the g is the function on the top. So now we have to take the third derivative of e to the 2z, okay, and get the result by placing z to replacing z by 0. So now the first derivative, residual this at z equals 0, okay. Now if the first derivative gives you, okay, let's take the first derivative, which is 2e to the 2z, okay. Now we take another derivative. Now one more derivative is going to be left over. So now it's 4e to the 2z. And then if you take another derivative, which is the final thing, just 8e to the 2z. Now at z equals 0, will give you just 8. Because e to the 0 is 1, and we get 8. Okay? Z to 4. But we forgot one thing, because we were going to do this 1 over n minus 1 factorial, which is 3 factorial. We forgot 3 factorial there. So that 3 factorial, which is 3 times 2 times 1, which gives you just 6. Okay? So there will be just 6 on the denominator. 6. 1 over 6, 1 over 6, 8 over 6 will give you just 4 over 3. Okay? 4 over 3 will be the result. Okay. So we obtained very nice result, okay, by just continuously taking derivatives when it is fourth order. So never forget this factorial business. Okay, good. Now we go on with another method, another example. Okay. I know this is a tedious algebra, but the experts, we have to go through these things. Okay. So now we will now calculate we will just start the integrals by using residuals, and you will see why do we have to learn all these things. Because suppose we will have to get this integral, like from 0 to 2 pi, okay, in a closed integral d theta divided by 5 minus 4 cosine theta. Okay, this is not an easy integral because there is no way you can use change of variables or something, because the derivative of cosine theta is sine theta. There is no sine theta on the numerator, so that there is a problem. There is a problem. So how can we calculate such a thing? Okay. Now what we will do is this. First, we will say that we will use all this. Z equals e to the I theta, and z to the minus 1 will be e to the minus I theta. So in order to write cosine and sine, okay, we will use this. We will use the property of e to the I theta plus e to the minus I theta divided by 2, which is equal to cosine theta. So any cosine theta and sine theta can be changed to exponentials, because exponential business is easy. So this is equal to, since this is z plus 1 over z divided by 2. Okay, but sine theta will be equal to just the difference between the two, z minus 1 over z divided by 2i. So sine theta and cosine theta can be replaced by this z, and then this turns out to be a complex integration, provided that d theta also should convert to something dz. Okay, something will multiply and we will get dz. In this case, this angle integration will be reduced to just the complex integration. Okay, so now we will have this integral will be written as, okay, now d theta. What is first? because we have cosine theta, okay, cosine theta given by that, okay, cosine theta is given by this, e to the I theta is z, don't forget. If you take dz, it's I times e to the I theta d theta. We can always use this property, okay? So now, but we have just d theta there. So d theta is just dz divided by, okay, I times e to the I theta. This is the numerator only. But the denominator is just 5 minus 4 cosine theta. But cosine theta is given by this expression. So 4 times cosine theta is 1 over 2 z plus 1 over z. Okay? And there is a parenthesis. See, this cancels that 2. And now you get now. Don't forget this is also z. Okay? This is z. So dz is I z d theta. You can also use this because e to the I theta was equal to z. So we have everything written as z, so that we replace this by z, okay, I z on the denominator, I z. Now, if you multiply everything, okay, this is the integration you will get. Okay, this is the integration you will get. So it will be equal to I integral, okay, dz divided by, okay, 2z squared minus 5z plus 2. Now, do you understand the reason why we learned this kind of equation? Because sine and cosine turned out to be some second order equation on denominator which blows up at some values, okay? At some values. So now, see, what are the roots of this? What are the roots? At 2, okay, 2, z equals 2 makes this 0, and z0 equals 1/2 also makes this 0. How can we get this? Okay, z0. So that's okay. So we can get the roots of this function very simply because it's 2z squared minus 5z plus 2. So when you set it to 0, you get the roots as minus b, which is plus 5. Okay, plus and minus square root of b squared, which is 25, minus 4ac. 2 times 2 is 4, 16. 16, okay? So basically this is just a number, not the complex thing, divided by 2a, which is just 4. As you see, 25 minus 16 gives you 9. And the square root of 9 is 3. So 5 plus and minus 3 over 4. So the first one is 2, because 5 plus 3 is 8. And then 8 divided by 2, 4 gives you 2. But 5 minus 3 gives you 2. 2 over 4 is just 1/2. This is how you can get the roots and then say that these are the simple. So this function can be written as, so the integral is I, okay, again, I'm not putting the limits intentionally because the limits from 0 to pi is for the integral only, but now we have dz divided by, okay, z minus 2 times z minus 1/2. So this is what we have. Now we have to be really careful if the angle, as you see, the angle is going from 0 to 2 pi. 0 to 2 pi, okay, and 0 to 2 pi, and what about the radius of this thing? Radius of this. As you see, the radius is the angle, the radius is just, the radius is just unit circle. Unit circle, the radius is just 1. It's just this, okay? In the complex plane, it's 1 here. Okay, I there, minus I and minus 1. So it's the unit circle. The angle is changing from 0, this is 0, and then this is like 45 degrees. And then it goes like that. So our curve is this, okay? The angle is going from 0 to 2 pi. But now let's check. which one is which one of these singularities included in this thing. As you see, the singularity z equals 2 is right there. So this is the singularity z equals 2. But this is not inside this chamber, which is the unit circle. But z equals 1/2 is right in the middle on the x-axis in here. So it is included. So this gives you problem. This gives you problem. Okay? This gives you problem. In this case, you have to take the residual of this function and treat this function as the numerator. So now this is written as I, don't forget I on the top. So 1 over z minus 2 times dz divided by, okay, z minus 1/2. So the residual is of this function is given by just 1 over z minus 2 evaluated at z equals 1/2. Okay, simply. So when we put 1/2, it's just, when we put 1/2 there, okay, you will get 1 over 1/2 divided by 1 divided by 1/2 minus 2 minus 3/2, or minus 3/2 minus 2 over 3. Minus 2 over 3 will be the residual. Okay, minus 2 over 3 residual. Okay, now what is the result for this function? So the integral is just 2 pi I times the total residual. But the total residual is, don't forget this I. There is another I there times minus 2 over 3. Okay, now i's will cancel. It will produce minus sign, and this minus sign will go away, 4 over 3 pi. So the result is 4 over 3 pi. As you see, the result happened to be just a real number, and then there is nothing like okay, let's see. The result is not complex and just 4 over 3 pi. So this result of this integral, okay, is just simply equal, the result is just 4 over 3 pi. Now, did you understand the reason why we go to complex analysis? This problem, this kind of problem is very difficult to solve, but by employing, okay, this complex property, then we can calculate this, and this is what we have done. Okay, so let's check again. So this unit circle, if the angle is going from 0 to 2 pi, it's the unit circle, only the singularity, which is at z equals 1/2, is included, and the rest is analytical. So 1 over z minus 2 is treated as the numerator, but the denominator is this. So now, except denominator, this function is evaluated 1/2, and this is what we get, and the result is going to be 4 over 3 pi. The result should always be a real number. If the result includes some kind of I or something, it means that you have made a mistake. So now, did you see how we were able to use this residual theorem and complex analysis to calculate such integrals? So for homework for you, for the study, I give you this. From 0 to 2 pi, okay, calculate d theta divided by 5 minus 3 sine theta square. Okay, don't forget, this will be, you can get the 0 by setting the whole denominator to 0, but now this will be second order. So second order means that you will have to take the derivative of the denominator twice. Okay, and now what is that? How can you get this integral? This is your homework. Okay, so please solve this at home and return me in by just taking the snapshot of the solution. Of course, always, whenever you return me some kind of solution in quiz or in homework, you will write here that I promise that I haven't gotten any information from my friends.